Okay, so once again, thank you, Celia, and of course for the introduction and for the invitation to give this seminar today. I'm really glad I can be here, and I'm going to present to you the talk titled Using the Varve Sediments Database, or for short, VARDA, to improve Bayesian Hdf modeling. So as the title suggests, my talk is broadly structured into two main parts. First, I will introduce you to VARDA and our efforts to synthesize and standardize data related to Varve Lake records. And the second part will concern to use this information we have already gathered to improve or critically inform Bayesian Hdf models to finally improve them. And just as a fair warning, I put an unreasonable amount of text in my slides, just in case that the connection goes bad or that my microphone goes shaky, that you are still able to follow my chat. Okay, let's begin. So VARDA, as an effort, is intended to not only provide proxy records from single lakes, so local lake records, but also to enable the connections between these different records to really build paleoclimatic networks, sensors of paleoclimatic change on a regional to global scale. And we were very happy to be able to publish our effort in ESSD. And everything I'm going to tell in the first part is described in very broad detail in this publication. So I just want to refer you to that. Okay, so we have published version 1.0, which allows detailed comparisons of published Varve records, including chronologies, tephra layer, radiocarbon measurements, and Varve thickness record. So you see, we focus first on all the chronological information which we could synthesize from lakes worldwide, and then to store this, so as first focus of our project. And now in version 1, the inventory includes 186 lakes with published Varve records. We have 95 lakes with available data, often with multiple data sets, of course. These include several chronologies, tephra layer, 14C measurements, and Varve thickness records. And if you look on the left here on the figure, you can see that the distribution of our archives is quite clustered with a clear focus on the mid-latitudes of the Northern Hemisphere. See that here, one big cluster in Europe and the second big cluster in North America, which is not very surprising, but still this shows that we still have large gaps in the database and the published Varve record also, especially in the Northern Hemisphere, which again exemplifies the need to include or to have more lake records to inform more global changes. And you see also that all our data sets for the chronologies, tephra layer, 14C measurements, and Varve thickness data broadly follow this clustering of the lakes, of course. So much for the spatial coverage. Let's come to the temporal coverage of our record. We see that if we combine all the data sets we found, you can see that here on the left with the chronologies and indicated by these bars, that if we combine them, we span the entire last glacial cycle, so more or less the last 120,000 years with these chronologies. Of course, on the lower end, we have quite short records like Lake Voserine of only 86 years, in total age span. Here on the longer side, you see records like Lake Malawi, which span up to 1.2 million years in Tanzania. This is, and here again, we can combine these different data sets to get, comprehensive, or to enable a comprehensive analysis of these records and jointly. Okay. You also see, if we look at the individual data sets which are included in version 1.0, that similar to this spatial clustering, we have this temporal clustering here in the Holocene or the glacial, a little bump, and in the Holocene period. So we see that also here there's a lot of research still missing for the longer time scales. On the other hand, we have quite a consistent picture here for the Holocene period with our database. The real innovative character of VARDA now is its data model. We use a property graph model, which is a connected data model that explicitly models connections, which you see here depicted as arrows, between data sets, which you see here depicted as colored circles, differently colored circles. And these connections allow to really construct paleoclimatic networks from individual lake archives. Just as an example, we can use event layers for synchronization, like tephra layer, for synchronization of different records using this model, which is really innovative, and we are really happy that our co-workers could realize that for us, with us. Now, we did not only collect a lot of data sets, but also we did an extensive meta information gathering, right? So for each data set, for example, here for the lakes, we collected metadata, or for the course, or for each data set, here, example of our meta information for chronologies. And we broadly let me say it like this, to make this graph structure work, we require a fixed amount of information concerning all of these data sets. So you see here, indicated by these green bars, the kind of meta information we need to include a record into our graph structure. And here, the yellow bars indicate additional information which may critically inform users of these data sets of their record and the associated meta information. Now, if all the required information is included well, we can model these graph structures in a broader sense as networks. So we can really construct custom-built paleoclimatic networks from these individual records. And that looks a little bit like this in the end, which is just an excerpt of our database. We just created this figure for illustration purposes. These are several European lakes, here indicated by blue dots, which are connected by common event layers like tephra layers. And of course, each lake is associated with data sets, which really enables this connection, this broad scale connection of individual records. Last year, with publishing the paper, we also went online. You can see the internet address given here. I would love to give you a little tutorial on how to use the internet page if there's a little time left in the end of my talk. But if not, if you're interested, in the meantime, just visit the page and you can try to build these networks from our Varve lake records on your own and for your demands, of course. Now you see the first version, as I already mentioned, the first version of VARDA mainly includes chronological data. And what we wanted to do is refining and updating all the existing chronologies which we could gather or synthesize from the literature. This had the goal to provide reliable chronologies which reconcile Varve counting with absolute age measurements, enable automated updates in the light of new information. For example, the InCal 20 curve was just released, giving the need to recalculate a lot of chronologies in the literature, or not the need, let's say the possibility of recalculating chronologies in the existing literature. And it would be just a great idea to have an automated way to do that, right, for all our chronologies. And then C, which proved to be the most trickiest part, to get some consistency in age uncertainty estimation. And what I mean by that, I will demonstrate in a couple of slides now with some examples we have in the database. So usually, Varve chronologies, as you may all know, are constructed in different ways, depending on the local setting and the need for constructing these Varves. A great majority of archives use, of course, Varve counting for Varve rate records and estimate uncertainties by multiple counts observers, for example, right? This is really a great, here's really a great example of that, of Kalanke et al., which was published last year, if I'm not mistaken, in GCRON, who could, by Varve counting and error estimation, really extract a reliable Hdf model, even in the light of conflicting radiocarbon measurements. Then other researchers might use Bayesian Hdf modeling. A lot of the researchers use nowadays Bayesian Hdf modeling to further refine their Varve countings. Here, an approach by 14 et al., I think, published in 2019, which, based on the lake record of Lake Iqaluit, came up with a novel idea to model Bayesian Hdf models from Varve counts. And a third, just recently published by Celia, used, for example, also in Bayesian category of Hdf models, the OXCAL with the U and the P sequence to get a reliable H model for the lake record of Dismere. Now you see, all of these approaches are very robust and really give a good estimation of H uncertainty and the accuracy of your Hdf model based on single lake archives, right? But in most of the cases, the efforts to construct such chronologies are really tailor-suited to these archives, which impede a little bit to extract or to make a refinable and updatable chronology as is our goal. And so we decided to not add to the mixture, this rich mixture of Hdf modeling routines. We tried to focus on a well-established Hdf algorithm. And that is, of course, the Bacon Hdf algorithm. Bacon has two major advantages from our point of view. First, it is well established and widely used across the palaeoenvironmental sciences. So that means that if we construct Hdf models using Bacon lakes, we have a similar nature in the estimation of uncertainties as, for example, have ocean records. And this makes it quite good for our purposes because it's comparable between the records and even archives. And the second major advantage of Bacon is that it has an explicit sedimentation model built into the algorithm, which in principle allows incorporating information from Varves into the Hdf modeling routine. And that's what we went for. So we wanted really to translate the Bacon algorithm to Varve thickness records to enable record-based Hdf modeling, but in a general sense. Just so we are all on the same page, I will just briefly introduce the Bacon algorithm. So everybody knows what I'm talking about, especially in regards to how we use it and how we can use it to translate between Varves and the Bayesian Hdf model. So first, Bacon slices a sedimentary sequence in equally distant segments, which you can see here. For example, this could be 1 centimeter. So each of these segments would be 1 centimeter thick. In a second step, Bacon models for each of these segments a random number of years which this segment contains. So the years per centimeter, for example, right? It does that not really, it does it really randomly, but according to a nice, really innovative model, in my opinion. And that's an autoregressive gamma walk. It's here briefly stated as a mathematical equation. And just to show what it means, you can see that this expression is divided into two terms, which are of significance for us. First, it's alpha, right? Alpha is a random variable, so a gamma variable, characterized by the parameters mean and shape. You see here what happens if you change the mean while synchronously holding the shape parameter still. It gets a little broader here, and with these gray lines, you can see that. And here you see what happens if you hold the mean of a gamma still and increase the shape. So your values get more clustered around your mean. It's a kind of variability and mean indicator for that. So to translate that, we have to estimate both of these parameters from a Varve record of Varve thickness data. And I just disregard this 1 minus omega term here. This is just used to hold the mean constant. I won't get into detail. The second major term in that equation is the left-hand side, which just indicates that any accumulation rate, so the number of years you see in a particular segment, is also a result of the preceding years, so the sedimentation rate in the preceding years. And how much these current sedimentation rates influence the sedimentation rates in the future is determined by this parameter omega. So, or let's just call it the memory in this equation. Now, Bacon does its magic by just realizing this model millions and millions of times, and through the magic of the Monte Carlo Hastings algorithm and MCMC operations, tries to find the best parameter combinations to fit your record given the absolute age estimations at hand, right? So the key to Bacon our key to translate Varve records into Bacon is that Bacon uses this Bayesian spirit, and where you can put in prior information about the accumulation rates in your record into the analysis. And you see both of these priors, which Bacon uses here in this screen. Right, but you have to know that this is more or less an uninformed prior. That means that if you don't really have any information about accumulation rates in your record, you can use this one. And this one was deduced by Goring et al. In 2012, published in 2012, I'm sorry. And he extracted these priors by analyzing 204 Holocene Hdf models from lacustrine and paleostrine environments in Northeast America, right? Now, our idea is to exactly take the road through the prior to give the Bacon algorithm all the information it needs from the Varve record, and use the accumulation rates observed in our Varve records as prior information for the modeling routine. Now, after really weeks of analyzing these equations, we finally found more or less the Rosetta Stone for us between Varves and Bacon, and we're able to analytically solve these equations to enable the estimation of parameters from a time series of Varve thickness record. And you can see the equations here at that point. Now, we started our analysis with this approach, but it soon became obvious that this is not the whole picture. Analyzing more and more Varve records, we became aware that if we only do it like this, if we only get the parameters for alpha and omega and then make one prior for the entire record, which your Varve chronology covers, leads to quite heavy deviations between the chronology and your Varve, your Varve chronology and the resulting Hdf model. And the reason for that is the frequent occurrence of change points in these chronologies. You can see that here exemplified by the Varve thickness record of Blue Lake in Alaska, and you see that really major shift in sedimentation rates here at around 1,200 BP. Now, these really impeded our efforts to integrate the Varve records into a single gamma function or a single model of Bacon. Now, but knowing that, we came up, so having all the necessary equations at hand and knowing about these change points and the occurrence, we came up with a new algorithm to extract these priors which you need for the Bacon routine from Varve records, and we called it a priori or Bayesian Hdf Modeling with prior information. Now I want to briefly guide you through what the algorithm does, just to get you acquainted with the idea and the algorithm. A priori starts by taking any Varve thickness record, right, as an input. So that's all that is required to give to a priori. Then, in the first step, a priori translated, so it segments your core into equally sliced segments and makes a change point detection. So our change point detection is quite sensitive. So our definition of a change point is a change point occurs if the mean accumulation rates of two segments here between these change points differ by more than 1 year per 100 years runtime. Actually, we tried different thresholds, but yeah, this one is the most accurate in terms of the resulting chronology. And it has to be so sensitive because many Varve chronologies are not associated with radiocarbon measurements, so absolute H-depth relations, which could somehow account for detecting such changes and eliminating the straight lines of our model. And we use for that the pruned exact linear time algorithm, or short PELT, which is an optimum algorithm, which is guaranteed to find all the change points in your time series. Okay, that's the first step in the a priori algorithm. The second, of course, is the parameter estimation based on the Varve thickness data in each segment. So we estimate the mean accumulation rate, the shape of the parameter for alpha, and of course the omega from the Varve record. Then in the third step, the simulation begins. We run the model with the estimated parameter and change points for several hundred thousands of times to assess a data model agreement. And we use for this agreement, or to quantify this agreement between the Varve chronology and our model simulations using an KS test. So we are always sure that what we are modeling really corresponds to the statistical distribution of Varves, how they were counted. Okay, and of course we can use this range of model simulations to come up with the high density interval of these models, meaning that we can say in this range there are 95% of our model simulations. So yeah, a kind of uncertainty estimate of our model. Now, of course, what's missing in that point is that we have no idea how the optimal delta D, so your slicing distance, should be. Should your record be sliced into 1 centimeter segments, or should it be sliced into 2 centimeter segments? And I think there is not really a good argument which can be made based on statistical or, I don't know, say methodological properties. So we iterated this. So we make an optimization. We use all the possible slicings of your core and always ask the question. So for each slicing, we do the whole a priori approach, estimating change points, estimating the necessary parameters, and so on, to get the model simulations at each slicing and to really have a look at the realism at each of these slicing steps, which you can see here. And this is the percentage of past KS tests. So where the alternative hypothesis that, the zero hypothesis that both your Varve record and the models come from the same probability distribution, is accepted. So it gives you a sense of data model agreement. And you see here that if we increase delta D, oh, I'm sorry, I forgot completely to mention that I will do this example at Lake Oeschinen, which was published by Aman et al. 2015. Really sorry. So if we increase now the interval for Lake Oeschinen, the record of Lake Oeschinen, we see that model data agreement really rapidly increases and gets its peak here at around 3.5 centimeters, in which almost 99.9% of all model runs correspond statistically to the Varve record or to your Varve thickness record. So basically, we could say we take all the models above this threshold of 95%. So just to make a hierarchy between the models, we use two additional informations. First, the mean uncertainty. So we want to select a model in which the uncertainty, the resulting model uncertainty, is never smaller than the counting error, which was recorded by the corresponding authors. So this is the second line of argument, which we could do to take one delta D over the other. And third, of course, the number of change points. Of course, for the sake of parsimony, we want to use as few change points as possible, right? So this gives another dimension of selection for the perfectly fitted delta D. Okay, like I said, in the example of Lake Oeschinen, it is 3.5. So what we can do now, we have all the parameters at hand. We only need to convert this relative time scale of the Varve counts to the absolute H scale. And this is first done by anchoring our high density region, so all the model runs, into the absolute H time scale, right? And we have three anchors for that. We can use an interval anchor, which gives uniform probability intervals, useful, for example, for surface anchoring, right? You can use a radiocarbon anchor to anchor your prior of the calibrated to the high density interval of the calibrated radiocarbon H estimation. Or third, you can use a Gaussian anchor, so a probability following a Gaussian distribution which is useful, for example, for anchoring your chronology or the model runs to tephra layers. Next, we just want to trim that. Now we want to look at your absolute H estimations. Here, in this case of Lake Oeschinen, these are several radiocarbon measurements which were taken throughout the core. And we can trim our high density interval of our prior range, right? The prior which we inferred from the Varve data, by just trimming, by only selecting those models which most agree with the absolute H estimations at hand. So the result is a posterior range, which is here in a slightly darker gray, which corresponds to the Varve counts in a statistical sense, right? They are realistic in that sense and agree with the absolute H estimation. So our best guess for combining Varve counting error with absolute H estimations. And you can see if we just anchor the Varve chronology of Ammann et al. Into this absolute H scale, that this high density region in this case corresponds very well to the Varve chronology, right? And here for comparison, I used Bacon, so the almost uninformed prior. I just used for this run the mean accumulation, which Bacon suggests in the beginning based on your 14C data, but with using the shape or the variability provided by the Bacon prior. And you see that it's the a priori approach leads to a real reduction of H uncertainty in most cases and a really reliable chronology and reliable estimation of H uncertainties. Right now, as you can imagine, not all of the records we analyzed are that easy to model because, I mean, the Varve chronology already agreed well with the radiocarbon dates before any modeling. Now, in other cases like the Shutter group, which I introduced earlier, we have this challenge of a disagreement between the radiocarbon measurements and Varve chronology. And that's mainly due to the reservoir effect for the upper part of these radiocarbon measurements, and of course, of counting uncertainties. So there's a little disagreement between the Varve chronology and these C14 dates, which are based on terrestrial plant remains and therefore are not that affected by the reservoir effect. And you see, if we apply a priori, we get or a priori faithfully models the Varve counts and is unaffected by the reservoir effect, and also accounts for the H for the counting errors and makes the best solution based on absolute age estimations and your relative Varve counts. Now, a second example which I want to show you a priori also works well in cases where we have floating chronologies, so where we don't have continuous Varve sediments up to the surface of your record. And in this case, which is analyzed, so the counting was done by Shuiru Shao. It's currently all of that is in preparation for publication. And yes, the Varve counts are from there. And we used a priori to come up or to resolve this disagreement between several tephra layers, C14 and C14 data. And we used a tephra layer here in this part of the lake of the record to anchor our chronology and to anchor the priors and to, due to the algorithm, to select only those suitable model runs which really maximize the probability of the radiocarbon measurements for our chronology. So we are quite confident that even for very difficult chronologies, that a priori in this works well. So you don't have to, or in most cases, hopefully you don't have to use a tailor-suited approach. We, of course, did that for all of the chronologies in our database, which we had for which we had Varve thickness data, right? And we asked the question, of course, that works well for Varve sediments, but can these Varve sediments also inform other records, for example, non-Varve lacustrine records, to infer a more realistic lacustrine prior for Varve sedimentation? And that's what I briefly want to show you now in the end of my talk. We see that the accumulation rates which we observe, that's the distribution here, not really mirror the Bacon prior, which was which was created by Goring et al. Right? In this comparison, we see that the Bacon prior underestimates the occurrence of these low accumulation rates of very thick layers, right? While overestimating the occurrence of higher accumulation rates, so that means lower sedimentation rates, so very slow, very small Varve couplets. Okay, so based on these observations, we of course could infer an a priori prior, so a prior which models the accumulation rates a little more realistic in terms of the observed Varve records. And we see that actually a K closer to 1 would be more realistic for Varve lake records. This, of course, increases the uncertainty in the record, but I think it could be worthwhile to include more uncertainty to really have all these individual lake chronologies fitting together. Okay. Second, of course, the memory prior. We again see that Bacon places a lot of density here, probability density in the high memory area, but we also observe these low memory, so just the low memory parts quite often. So we also can make an adjusted prior which models the observations a little bit more realistically. And of course, we can look at change points, and we can see that these change points occur frequently throughout in the Varve sediment profiles. So on average with 1.5 change points per kilo year for the records, and that they are therefore an intrinsic feature of these chronologies, which greatly enhance the realism in terms of data model agreement, and that they occur quite irregularly. Like you can see here on the left, you have these transparent rectangles, and if they overlap, so that is the uncertainty from one change point. So the age uncertainty of the dating of that change points, and if they overlap, we see a more synchronous response by these, or the more synchronous occurrence of change points, indicated by these darker blue colors, and lighter blue colors indicate that there's only one change point occurring at that time in our records. So these irregular occurrence throughout the Holocene impedes really the inference of general occurrence patterns for change points. And this is, of course, in a way sad, because we can't offer a more realistic point to model these change points for in instances where your record isn't Varve. But also it's a little bit a happy notice, because each lake has a unique story to tell. And again, this really demonstrates the need to have a lot of records to make paleoclimatic or paleoenvironmental inferences based on many records instead of just a single one, right? And that's what we want to achieve with VARDA. And here's a little outlook. It's our roadmap for 2021. We, of course, will provide the updated chronologies, which I just introduced to you, including a free version of a priori, so you might use that for your own research purposes. And I would be very, very happy if I could get if we could get feedback from the community for this app. I'm sorry. Then a second major step, there is the upload of proxy records. Well, first up here is a comprehensive set of 19 stable isotope records from Varve, and also including some non-Varve lakes. So these are oxygen and carbon isotopes, which will be imported shortly. Then third, we want to offer an import tool to really facilitate the community participation and to enable this collaboration within the community. And fourth, of course, coming up is an advanced visualization tool for lake-based proxy records. Okay, last but not least, before I say thank you to you all, to the audience, I want to really thank you, thank 4 persons especially for their invaluable help throughout this process. They really kept this going. This is a really big project, so I'm really happy about your support, your ongoing support from Alexander Braus and Marie Dorn, who are really the architects of VARDA, and all of the standardization efforts and the technical infrastructure of VARDA is really their work, right? Then I want to especially thank Laura Schley, who helped me with developing and programming the a priori algorithm. And without her help, I couldn't have finished that. And of course, last but not least, Achim for his support and the realization of this project, and VARDA, of course. And now, thank you, all of you, for listening, and I'm happy to answer any questions.